Thank you for taking time out of your day to look at what I call memory-efficient Java. This is normally like a 90-minute talk or 60, 90 minutes, but we'll try to take out the useful bits here. Marketing slide, you can read all the stuff. Co-founded Jay Clarity Performance Tooling, done a lot of work in the memory space. As part of Jay Clarity, recently acquired by Microsoft. So now we're part of the core Java engineering team within Microsoft that they have spun up, which kind of sounds weird, but it's actually been really, really cool. We've been able to do a lot of really fun, cool things. Okay, I'm going to start the talk out with this little bit of demo bit here. Now, excuse me as I bounce around because since it is a performance benchmark, and we're going to look at performance counters and stuff like that, I have to go into a slightly different setup for doing it. So I have this little toy game that I've actually been using for years just to play with. Mastermind. Maybe you remember it as a game as a child. It's, your friend picks colors, hides them from you, you guess. And as you make guesses, then your friend scores, and eventually, hopefully, you make the right guess, and everything is good. So in this case here, I'm going to use numbers instead of colors. And in this case, we have 100,000 choose 3, which is our solution space. So I've picked one, and I've been telling I'm now telling the application, okay, go find the one that I picked, and there's some scoring algorithm in there that basically says how close things are. So part of the whole process is actually trying to look at what the CPU is up to. Let's shut that down so we can see how that's working. And this will take a little bit to run. So while it's running, I'll just run back through the other bits of what we want to talk about. I'll come back to this in a second. See what's going on. Okay, so that's the start for our demo. And so the thing that we're trying to answer here is what is the performance trouble spot in this particular application? Now, from the title of the talk, you can probably guess it's going to be memory, but let's see how that works out. And so here's a question that's been asked, right? What is your performance trouble spot? And this is an industry survey that a friend of mine did, and he wrote this really nice report, and it looks really cool. You can see that databases show up quite frequently in this chart. The funny thing is that the thing that doesn't really show up is this thing called excessive memory churn. You see it's only 10.56%. And this is really a function of the visibility that we have in our systems. In other words, this is a problem that we all have, or what we saw in our experience is that approximately 70% of the applications that we looked at have, but it's completely invisible in the sense that it's happening and no one sees that it's there. And the strange thing is everybody is so focused on garbage collection that that they'll think of it like, oh, this is a GC problem. And the answer is no, it's actually not. It's a memory efficiency algorithm, memory efficiency issue with the algorithms that you're using. And it's been backed up by a little bit of rhetoric saying like, go ahead and allocate. Allocations are free. Well, not allocations free. Garbage collection is free for things that you allocate and throw away. And that's the truth. The garbage collection for young generational collections is free for garbage, but it still costs you something to get it there. So where do we see these problems show up? Well, they actually show up in like a whole list of what I call excuse me, third-party products. Apache Spark is a special case because in this particular case, it's written in Scala, and writing things in Scala or Kotlin come with their own challenges for the optimizers. So even if you do something that in Java, the JIT compilers would look at it and say, ah, okay, I know what you're trying to do there. I'm just going to unbox this thing. You no longer get an allocation. We can just drop the particular value that you want as a scalar right in the code, and we don't have to worry about any heap allocations here. Unfortunately, the JIT is not good at recognizing these types of patterns when they happen in alternate languages that run on the JVM, which is why Grail VM is an interesting project. And let's not pick on anything in particular. This just pretty much happens all over the place, right? So I just go through the list, and so on and so on and so on and so on and everything like that. But if you're using any of these frameworks, then you're very likely in this, very likely that your application is suffering from high memory churn. So let's go quickly back over to our application and see what's happening over here. And as you can see, just make this a bit bigger for you to see. You can actually see that, oh, okay, the CPU has been running. It's been mostly in user space. That's the green bits as opposed to the red bit. So algorithmically, everything's been happening the way it should. And it's taken about 90 some odd seconds for us to find the answer. So the question is, like, if we need to get the answer faster, how are we going to be able to do that? Well, we need to find out what's happening in the green bits here. What are our threads doing here? The first thing I'm going to check for is to try to sort out, okay, do we have an allocation issue here? So I'm just going to bring up some tooling here. Okay, we don't need that anymore. I'll drop it. And oops. Oh, great. Okay, we're in the wrong spot. Let me go and figure out where did it go to. There we are. Sorry. That, there, and there is our. Somehow we're supposed to get a GC log here, and somehow we've lost it. Okay, so assuming we had a GC log, what you'd be seeing for this application is, I don't know why we don't see one. It's kind of weird. But what we'd actually be seeing is an application. Okay. What we'd be seeing is an application that's allocating approximately 14 or 15 gigabytes per second, right? So there's an excessive amount of memory churn here. Right, so, and just what is the impact of this memory churn? Well, here's some war stories, you can read them. But the one thing that you can consistently say about the war stories is that when we start reducing memory churn, we get orders of magnitude improvements in performance in most cases. So we don't tend to get the 5% or 10%. These things of getting like 2x or 4x are just things that we're fairly consistently seeing across the board. And that's how big a problem this is. So which is really, in my mind, makes it amazing that it's not as visible as it actually probably should be. So when we looked at Mastermind, we're basically saying, okay, this is allocating about 16 gigs per second. The question is, what is a reasonably good allocation rate? Well, from our estimation, we see reducing the allocation rates is actually working on this, what we call it, like a power curve. And there's about a 1 gig per second threshold where once we get below that, we're pretty well tuned. In other words, that you start seeing diminishing returns from reducing the allocation rates. So just what is it that we're looking for? Well, what we're looking for are these types of things, these allocation sites, right? And since allocations will mostly occur in Java heap, what we're doing is we're trying to find where these things are and then see if we can take them out of our code. Now, the funny thing with profilers will tend to disturb the runtime. And as they disturb the runtime, what they'll do is they'll cause the JITs to actually not scalar replace the allocation site. So you won't get this allocation site elimination happening. And so some of the profilers will actually, in this case, lie to us. So I think with that, what I'd like to do is just flip back over to our application and just sort of drop into some tooling here. So the first thing we need to do is get this thing running again. Okay, and the first tool I'm going to touch is Visual VM. So Visual VM is a free open source tool. It's been around for a number of years, and in this case I got the latest fresh version just last night, so I don't have a lot of my plugins installed here, but we do have the things we need. So what I'm going to do is I'm going to find the application. I'm going to attach to it. I'm going to go to the profiler. I'm going to go to memory settings. I'm going to say find all of the classes, find all of the arrays, track only live events. I'm going to limit the, I'm going to collect the allocation stack traces, but I'm going to limit them to a depth of 10. A depth of 10. Attach, and I'm going to start the application running. So we get something happening here. So I'm going to run this thing. And so I'm looking for, in this case, a frequency issue, right? So really we're talking about rate versus frequency. And the allocation rate is what I consider to be like megabytes per second. Frequency is how often am I actually hitting an allocation site. And I'm going to be able to use the allocation rate as an approximation of the allocation frequency because most Java objects are approximately the same size. Now, sometimes you get some big things being allocated, but that's just what I call noise in the estimation. The reason why I'm interested in frequency rather than rate is because the cost of allocating these small objects is mostly the same as the cost of allocating a much larger object. It's only when you get into really large objects that it starts getting to be slightly more expensive. So based on the cost of an allocation is constant, then I'm really looking at frequency because, a single allocation is cheap, but cheap times many equals expensive. So in this tool here, when I look at, going back to here, if we look at Visual VM, we don't actually have a frequency calculation, but what we do have is sorry if I can get this thing to actually function. No, it's not going to. What we actually do have is we have allocated objects. So I can sort by allocated objects, and what that does is it gives me a proxy measure of the allocation frequencies here. And you can see in this case, our big allocator is int, and if I tunnel in, I can see I have an equal contribution of big int and this array copy range, so we can basically take a look until we hit application code, which is this index class where it's taking a remainder. And if we look at this thing here, we hit application code add index.remainder. Comes from this other method called calculate index. Calculate index is in this arrangement group class. So now you can see from here, I have a really good clue as to where I want to go into my code and start looking at the algorithms and see what adjustments I can make to try to improve the memory efficiency of it. Okay, how much time do we have here? Are we running over yet?
No, we still have time.
Yeah, we still have a couple minutes, I think. Yeah, okay, cool. Because the problem with Visual VM is it's profiling from outside of the JVM, so it's basically a Java application that's instrumenting your code. and quite frankly, it lies to you sometimes. There is an object in here that shows up called score. And I know score is one of these objects that is actually can be scalar replaced very easily. And not only that, well, in this particular profile, it's not going to pop up till a little later on, but eventually it'll become the #1 allocated object. But I know it's not being allocated on the heap, and that's because of how this particular profiler works. So if we just stop profiling here, let's turn this off. What I can do is quit Visual VM. We can bring up another tool called Java Flight Recorder. Now, Java Flight Recorder records things very differently. It's instrumented inside the JVM. So the console here that I'm bringing up is Java Mission Control. Java Flight Recorder is a different component. It attaches to the JVM. Well, it works inside the JVM, and so you can turn it on, and you can get recordings from it. The console would then read the recording and then work with it. So in this case here, what I'm going to do is I'm going to go to the JVM browser. So it's finding all of the JVMs I can attach to. I'm going to attach to the, I can attach to the server where I can just say, okay, let's get a flight recording. Brings up a wizard. So this is one way of starting it. Another way of starting it is, of course, you can start the recordings from the command line, or you can use another command called jcommand, or if you have a tool that allows you to attach to the mbeans that are exposed by the JVM, then there's mbeans that actually control flight recorder, and you can configure it that way. So there's many different ways you can do it. Okay. So I'm going to record for 1 minute. I've turned off a lot of the settings here so that I'm just looking for allocations and promotion. That should reduce the overhead. The overheads here are going to be very small anyways. There's some templates that I can actually use. I won't go through that because just from time constraint, but there's templates here that you can use to configure and define your own custom events and do things. Anyways, so I'm going to run this. It's going to take a minute of runtime. And we can see that our application here is still running. Sorry if my voice is running out of sync with the video. This is actually running on a different laptop, so the video is being streamed through. There is a bit of a lag here. Oh, it's done. Wow, okay, so let's just clear and run it again. Right. I have actually not been looking for questions, so I don't know if they've actually come up.
Yeah, we don't have questions just yet.
Excellent. Okay, that's good. Now I'm trying to get back to there. Okay, so 6, 5, 4. That gives you an idea what the lag is. 3, 2, 1. There. So it's 5-second lag. Wow. Okay, excellent. So now we're going to open the recording. So what I'm going to do is I'm just going to shut down Sensum so we can see the recording. Could not retrieve aptitudes for recording. Maybe I shut it down too early. I hope not. Anyways, so if we look at the memory analytics here, you can see that the int array has come up as total allocation as being 377 gigabytes. And you can actually now see the sources of where that int array is being allocated down here. And so again, I have a really good clue as to where I can go look in the code and try to improve the memory efficiency of this particular application. Of course, index, we saw that class show up, and it actually shows up here also. Surprisingly enough, oh yeah, score does show up here, and I'm running in JDK 14, and so this is a bit of a mystery, is that I don't know why score is showing up in this profile. In my experience, it shouldn't be. I don't believe it does in JDK 8, so there might be some sort of regression in terms of what the JIT is doing here. which will be of interest to explore at a later time. Okay, anyways, so I think I've actually run over a bit of time. So what I'll do is I'll just say, you know, the next step is really to go into the application and start making changes to the application. When we make all of the changes to this application, that runtime actually, in this case, drops down to approximately 12 seconds. Just to give you an idea of what the performance improvement would be for this particular application.